Hello students, welcome to the second lecture on Maclaurin series. So in this lecture we are going to illustrate examples by using some standard Maclaurin series. So first example is using Maclaurin series show that e raised to x cos x cos x is index of exponential, e raised to x cos x is equal to 1 plus x square by 2 minus x cube by 3 plus plus plus. So now to address this question we need to know, let e raised to x is equal to it is not let, it is we know that e raised to x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Similarly, cos x is 1 minus x square by 2 factorial plus x to the 4 by 4 factorial minus x to the 6 by 6 factorial plus and so on. So we can easily write that therefore x into cos x is x minus x cube by 3 factorial plus x to the 5 by 4 factorial minus x to the 7 by 6 factorial and so on. Now let x cos x equal to theta. So e raised to x cos x will be 1 plus theta square by 2 factorial plus theta cube by 3 factorial and so on. See, this theta comes in picture because I am treating this x cos x as theta, so this comes in terms of theta. Now I am going to replace theta by my original x cos x. So x cos x plus 1 by 2 factorial x cos x square plus 1 by 3 factorial x cos x cube and so on. This is equal to 1 plus. Now look at this x cos x. What is x cos x? X cos x is x minus x cube by 2 factorial plus x to the 5 by 4 factorial minus x to the 7 by 6 factorial, right, plus and so on. I should not write like this, plus now square of this term. So x minus x cube by 2 factorial plus x to the 5 by 4 factorial minus and so on. It's a square, but then there is a coefficient 1 by 2 factorial, this coefficient, plus 1 by 3 factorial x minus x cube by 2 factorial plus x to the 5 by 4 factorial and so on it's a okay. I am going to write this in the next line. So plus 1 by 3 factorial x minus x cube by 2 factorial plus x to the 5 by 4 factorial minus x to the 7 by 6 factorial plus it's a cube and so on. Now let us look at this series in the ascending order. So e raised to x cos x. Now how many constant terms are there? So in this series this is the only constant term, so I am going to write it here plus. Now how many coefficients of x are there? So this is the only term with x, so I am writing it as it's a coefficient, right? Now plus how many square terms are there? So if you observe this, there is no any coefficient of x square. If you observe this, there is no any coefficient of x square, but there is a x and there is a square outside a bracket. So first term whose coefficient is 1 by 2 factorial is of x square in the second bracket, 1 by 2 factorial x square, and there is nothing in the third bracket of order 2, and same thing for the higher orders, for the higher terms. Now let us look at cube term. So I have one cube term in first bracket with coefficient minus 1 by 2 factorial. So I am writing this as a minus 1 by 2 factorial. In the second bracket there is no any cube term. There is a cube term, but it's a square, will give you 6. So there is no any cube term in the second bracket. But if we observe third bracket, so first term in the third bracket with power 3 gives you x cube, and its coefficient is plus 1 by 3 factorial x cube. Although there is x cube in the third bracket, but this is x cube is not only x cube, is a x cube with cube of a bracket, so that will be no more x cube, it will goes to some higher powers of x and so on, right? Now we rewrite this. So e raised to x cos x is equal to 1 plus x plus 1 by 2 factorial is 2, so x square by 2 plus minus 1 by 2 plus 1 by 6, 3 factorial is 6, x cube plus and so on. And this is equal to 1 plus x square by 2 plus, so this is minus 6 plus 2 by 12 x cube and so on. 1 plus x square by 2 plus, now this is minus 4 by 12, so that is not plus, it is minus 1 by 3 x cube plus so on. So this is a required expression, and keep in mind that we have used some basic known Maclaurin series of some standard functions. So this is what e raised to x cos x is. Now let me discuss one more question, question number 2, and that question is write the Maclaurin series, write the Maclaurin series of root of 1 plus sin x. Now for this I am going to take help of sine 2 theta will be 2 sine theta cos theta. Now I am going to put theta equal to x by 2. So left side will be sine, this 2 goes away, and sine x equal to 2 sine x by 2 into cos x by 2. So my given function f of x, which is equal to root of 1 plus sine x, with above substitution looks like 1 plus 2 sine x by 2 into cos x by 2. This product of 2 times sine x by 2 and cos x by 2 gives rise to the adjustment that you can write this 1 in the form of addition of two functions, such that we will get complete square in the square root. So with the help of that 2 sine x by 2 cos x by 2, I can write this 1 as sine square x by 2 plus cos square x by 2, right? Therefore my root of 1 plus sine x will be root of sine square x by 2 plus cos square x by 2 plus 2 times sine x by 2 into cos x by 2. Now if you observe this root, so it's a complete square, and it's a complete square of sine x by 2 plus cos x by 2. So root goes with a square, so that gives you sine x by 2 plus cos x by 2. Now sine and cos are standard functions, and their Maclaurin series are, Maclaurin series of sine is plus, so this is Maclaurin series of sine x, and I am replacing x by 2, plus n is from 0 to infinity minus 1 to the n, x by 2 to the 2n divided by 2n factorial. So if you want to illustrate it further, you write it in the ascending powers, that is terms of x, terms of square, terms of cubes, and so on, if you want to illustrate this more. But idea is you can use the standard expansion of Maclaurin series in this type of evaluation. I hope this problem is okay to all of you. Now I suggest you to go from Maclaurin series of this function. So write down the Maclaurin series of sin x, although we have used this series in the problem, but I want you to go through this. Sin x, cos x, tan x. Tan x is little bit tricky to evaluate because there are so many complicated derivatives, but try to evaluate it up to the fourth degree of x. Then look at hyperbolic, sin hyperbolic x, then look at cos hyperbolic x, and then you will find a nice pattern between this sin x and sin hyperbolic x, similarly cos x and cos hyperbolic x. Then look at a raised to x, then look at 1 divided by 1 plus x, then 1 divided by 1 minus x, and try to write the standards, try to write the Maclaurin series of all standard functions. That will give you idea uh, of the patterns which are coming in the series. So with this I am going to stop here. So please try to work out all these examples. Thank you.